Hi, I'm Alicia. I'm a grad student at University of Toronto with Bart Ruperta and Norm Murray, and I also work really closely with Daniel Grosjean. And my title is really long, like Dimitri just said, but I prefer to call it Making Reconnection Cooler. Thank you for that. Thank you. Okay. So we've heard a lot about the X-rays that come from AGN from several people, especially Chris did a really good job explaining it today. But around accreting black holes like X-ray binaries or luminous active galactic nuclei, there's this layer or region with very hot, very dilute gas called the corona. And we don't really know what the geometry of the corona looks like other Chris explained. But we know that it is a source of bright X-ray emission. So here we can see, is this a thing? Yeah, okay, thanks. That there is some hard X-ray emission that peaks around 100 keV for both XRBs like Cygnus X1 and luminous AGN like NCG4151. And so this X-ray emission in the hard state is thought to be produced from inverse Compton scattering off of softer seed X-ray photons. So the X-ray, the hard X-rays are thought to come, like I said, from this inverse Compton scattering, but it's also thought to be powered by relativistic reconnection. So in the case of a accretion disk like the Shakura-Sunyaev type, so there may be these little magnetic loops around, and those loops may be reconnecting in the relativistic or in the radiative regime. And we also see reconnection happening in simulations of mad or truncated disks. So this is a simulation from Jibwa Masoki at CITA, and she is simulating a cooled disk here. And if you zoom in on the region around the black hole, this region here, you can see a long current sheet forming in the corona. And she also sees that there is flux decay happening very often with reconnection events. So radiative reconnection is pretty well understood in kinetic theory and PIC simulations, but it's not properly done in global GRMHD simulations yet. So what I'm focusing on is, I'm basically taking a small local box here of essentially a single current sheet with corona-like plasma, and I am applying a radiative model to that in MHD to see if we can match macroscopically what PIC produces. So in order to make this subgrid model for the cooling, the first thing I have to ask myself is, where do I want this cooling to take place in the current sheet? So I want a cooling function that will pick up basically where it's hot, and that'll be in X points. And the cooling that's happening there is inverse Compton scattering, so very high relativistic electrons are upscattering photons. But I also want it to pick up where things are moving very fast. So that would be in the outflow or the plasmoids. And here, this corresponds to basically the bulk flow of the plasmoids themselves are upscattering the photons to higher energies. So last year, Daniel found that in a turbulent box in PIC of the corona, that the bulk motions of that turbulent box could reproduce the spectrum seen from Cygnus X1. And these bulk motions are well within the regime of MHD. So you might be wondering, and some of you have actually asked me this before, but I'm saying I want to reproduce a kinetic result with MHD, and the context I'm thinking about is reconnection. So you might be thinking, why would you do that? Because we know that an MHD reconnection is way too slow. In PIC, the reconnection rate is 0.1, but in MHD, it's 10 times slower. So can I even do a meaningful comparison between PIC and MHD when the reconnection rate isn't the same? And the answer to that is yes, because of what Lorenzo discussed yesterday, this non-uniform resistivity model. So he explained it really well yesterday, but I'll just quickly recap. Basically, the fast reconnection rate in PIC comes from an anisotropic electron pressure, where you have like this pressure gradient from the upstream down into the sheet. And we're able to model this in MHD using a non-uniform effective resistivity localized to the X points. So the non-ideal field, is given by this with this effective resistivity, and then the current you plug into that comes from the charge starvation that Lorenzo explained. So this is basically just saying that charges are moving out of the X points so quickly that there are very few charges there, and so the current in that limit is given by NEC. But N isn't really a meaningful thing to say in MHD language, so we switch that to a mass density. And then we're left with this charge to mass ratio, which we call delta, and now this is a subgrid model for the skin depth. So this theory has been worked out and written up by Abby Moran, but it's starting to be, well, it has been implemented in MHD code by Bart, and also Michael, who's going to talk next. So you can see here, comparing the non-ideal field in PIC in the top to this new non-uniform resistivity, and then compared to the old uniform resistivity. And you can see that non-uniform and PIC match quite well, and that you do have this high resistivity in the X points. But what's really exciting about this is the reconnection rate. So in the uniform resistivity model, the reconnection rate is down here in blue, and the PIC reconnection rate is up here in yellowish. But now with this effective eta, you get purple, which lies on top of the PIC. So we're able to recover that 0.1 rate. So now for how I model the cooling. So in kinetic theory, Heike explained this really well too, but the radiation is essentially modeled as a radiation reaction force, or a drag force, given by this equation. So this depends on URAD, the background radiation field, and then gamma, the particle Lorentz factor. So as Heike explained, you can re-parameterize this in terms of a gamma rad. And the way to do that is by considering the force balance between the electric force and the radiative drag force here. So this is something that looks like this now. So this is basically saying you are accelerating the particles from the electric field up to this characteristic gamma rad. So then if I take the U rad from this equation, plug it back into the drag force, you're left with this. So now we have a way to write the drag force in terms of this gamma rad, which can control the cooling strength. And so this is what is subtracted off the Lorentz force in PIC when you're modeling cooling. So now I need an analogous way to do this in MHD. So instead of a drag force, we are looking at energy and momentum sinks. So the form of the sinks that I'm using come from Golan and Levinson, and they're kind of a lot, but I can explain them better later if you'd like. So this is the energy sink, this is the momentum sink, and what's new here is we have this big gamma, which is the bulk Lorentz factor, and then we have this beta gamma, which is the bulk velocity, and then we have theta instead of the little gamma, which is your dimensionless electron temperature. So I want to do a similar force balancing thing here to re-parameterize in terms of now a theta rad like I did in PIC. So if I consider this current sheet, I'm going to balance like the energy fluxes in and out of it. So the flux entering this current sheet is just the Poynting flux over 2, because half of it gets dissipated away. And then the flux leaving the current sheet is basically the inverse Compton power times the number density times the thickness of the current sheet delta. So we can write an expression for delta if we combine Ampere's law with this charge starvation that I was talking about earlier, and it will give you a relationship like this. And then the other thing we need to get rid of is this gamma rad, because this is MHD. So we just use gamma squared equals 12 theta squared, which you just get from averaging over the Maxwell-Unier distribution. So this is a lot of math, but if I balance those two fluxes, you're left with an equation that looks like this. So now this is what the PIC force balance looked like, and this is the MHD energy balance. So these are actually equivalent. The only reason they look different is because here I have theta rad, but if you just sub gamma squared is 12 theta squared, these are exactly the same. So we're actually able to recover the kinetic cooling theory in MHD with this non-uniform resistivity model. So now I want to reparameterize by taking this URAD in the same way I did for PIC. So if I plug that back into my energy and momentum sinks, I'm left with my final cooling law. So remember I said I wanted my cooling law to pick up high temperatures and fast velocities. So these are my final equations. And so I do have this theta squared, which is picking up the high temperatures, and this beta squared, which is picking up the bulk motions, and it's now parameterized by this theta rad in the same way that we parameterize the PIC equation by gamma rad. And these are equivalent if you use the fact that gamma squared is 12 theta squared. So we are able to measure the cooling in the same way in both simulations. So I really wanted to focus on the analytics in this talk because I thought they were very exciting and interesting, but we have implemented this model in the MHD code and are comparing it to PIC, and I do have some preliminary results from like 2 days ago. So here is the model implemented in MHD. The code I'm using is Bach. On this side, I have the not cooled case, and then this side is the cooled case. And this is just a regular current sheet in relativistic resistive MHD. And then the third R here is for the radiative, which is what I'm adding. You can look at the specifics here if you're interested, but basically this cooled case is for very strong cooling, so it should be taking away a lot of temperature essentially, which is what you do see here. The temperature is much lower on the cooled side. And you can also see like the charge derivation in the X points pretty well here too. And that is everything. I'll just leave with this summary slide, which also shows this little movie of another cooling case. So to summarize, hard X-rays observed from black hole corona could be powered by reconnection. I've developed a cooling model for inverse Compton scattering on both thermal motions. So this panel here is showing my energy sink, my thermal cooling law, and then here's the temperature. So you can see it is picking up where it's hot and cooling where it's hot. And then I also wanted to cool on the bulk motion. So here's my bulk cooling law, and here is the bulk motions. And again, it's picking up where things are moving fast. And with this new non-uniform resistivity, the effective eta, we're able to analytically recover not only the kinetic reconnection rate, but also the cooling in MHD. And we're currently implementing and running this in MHD using Bach and PIC using Tristan V2 to compare the two and see if it's something that we could implement to make global simulations a little more realistic. Thanks.
Thank you. Thank you. Questions, Heike?
Thanks for the great talk, Alicia. I have a question about, so the cooling prescription you have is essentially as soon as you radiate, it's a drag force, right? So your photons just leave the system. But in principle, in some of the realistic scenarios, your optical depth can be marginal or high. So your energy still remains in the system and redistributes simply. So have you thought about having some prescription which would take you from low optical depth to high naturally?
Yeah, thanks, Heike. So essentially, we're throughout my PhD, we're going to try out a few different cooling prescriptions. So this is one of them. But after this, we're planning to go to M1, which would cover that regime a bit better. And then compare the two, see which one reproduces PIC better.
Thank you. Lorenzo?
Nice talk. Thank you. This is more like a curiosity, and maybe is in the movies, and I did not appreciate it. So one thing that we saw in PIC with strong relative losses is that within the plasmoids, 2D, okay, the particles are essentially evacuated from the front side and advected towards the back because they're seeing the photons coming from the forward direction. And I was trying to see whether you see the same thing. Maybe it's worth going back to the movies. So for the strong cooling versus weak cooling. But I don't know if you have anything to say about that.
I made this movie yesterday. So that is the extent of the analysis I have done on the simulations. But I guess you do see this. Yeah, the top is density, sorry. So it does look like it's on either side of the plasmoid pretty low. But that's something I'll keep in mind as I finish it up. Thank you.
Thank you. Any other questions? Okay, in that case, let us thank Alicia again.